Welcome back to GeoMethod. If you enjoy clear visual geometry proofs, consider subscribing. Here is today's challenge. Why is the angle bisector length theorem true? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Let us prove the angle bisector length theorem in standard triangle notation. In triangle ABC, point D lies on segment BC, and segment AD is the internal angle bisector. Write segment BC as segment A, segment AC as B, and segment AB as C. These are the sides opposite A, B, and C respectively. The base pieces, segment BD and segment DC, are M and N, and the bisector segment AD is X. The angle bisector theorem says that the two base pieces have the same ratio as the two adjacent sides. Since segment AB is C and segment AC is B, M over N equals C over B. We also know M plus N equals the whole segment A. First insight: the ratio and the total determine both pieces at once. Divide the total, segment A, into C to B shares. The first piece, M, is segment A times C over B plus C, and the second piece, N, is segment A times B over B plus C. Now, mark alpha at B. Since D lies on segment BC, the directions segment BD and segment BC are parallel. In fact, the two rays coincide, so triangle ABD and triangle ABC use exactly the same included angle alpha. Apply the law of cosines to triangle ABD. The side opposite alpha is x, so x squared equals c squared plus m squared minus 2cm cosine alpha. Apply the law of cosines again to the whole triangle ABC. The side opposite the same alpha is b, so b squared equals c squared plus segment a squared minus 2 segment a times c cosine alpha. Second insight: both cosine law equations contain the same cosine alpha. Rearrange the equation for triangle ABC. 2c cosine alpha equals segment a squared plus c squared minus b squared, all divided by segment A. Because both equations contain the same cosine alpha, substitute that expression into the equation for triangle ABD. Now, x squared equals c squared plus m squared minus m over segment A times segment a squared plus c squared minus b squared. The trigonometry has disappeared. For a cleaner exact derivation, let s equal b plus c. This single symbol will keep the next formulas readable. Because m equals segment A times c over b plus c, the new notation gives m equals segment A times c over s. Insert m equals segment A times c over s. Then x squared equals c squared plus segment a squared times c squared over s squared minus c over s times the quantity segment a squared plus c squared minus b squared. Regroup the expression into two visible cancellations. We obtain x squared equals c squared minus c times c squared minus b squared over s plus segment a squared times c minus s over s squared. For the first cancellation, use s equals b plus c. The difference c squared minus b squared is c minus b times s. For the second cancellation, since s equals b plus c, c minus s equals c minus open parenthesis b plus c close parenthesis, which is negative b. The side-only terms collapse to b times c. The remaining term is negative segment a squared times b times c over s squared. Therefore, x squared equals b times c minus segment a squared b times c over s squared. Now multiply the two base piece formulas. M times n equals segment a times c over s, times segment A times B over S. So m times n equals segment A squared times B times C over S squared. Replace that repeated fraction by m times n. The compact result is x squared equals b times c minus m times n. If only the three side lengths are known, substitute the product m times n. This gives x squared equals b times c minus segment a squared b times c over the square of b plus c. Factor b times c. Equivalently, x squared equals b times c times 1 minus segment a squared over the square of b plus c. Combining the two terms gives one fraction. X squared equals b times c times the square of b plus c minus segment a squared all over the square of b plus c. Because x is a length and b plus c is positive, take the positive square root. This gives x equals the square root of b times c times the square of b plus c minus segment a squared divided by b plus c. Finally, factor the difference of squares. The numerator becomes the square root of b times c times b plus c plus segment a times b plus c minus segment a. Therefore, for an internal angle bisector, x squared equals b times c minus m times n. In this figure, segment AD squared equals segment AB times segment AC minus segment BD times segment DC. The final answer is x squared equals b times c minus m times n. If you found another construction, share the key move in the comments. If this proof helped, subscribe for more geometry explained step by step. Thanks for exploring geometry with GeoMethod.